Hello and welcome back. We are in Chapter 7 of Atomic Models for Diffusion, where we will investigate the atomic basis for diffusion. So in Chapters 1 through 6 in the book so far, we've been treating diffusion as a macroscopic process in terms of continuous equations and a macroscopic diffusion coefficient. Today, what we're going to do is acknowledge that all materials are made up of atoms, and if you look underneath the hood, what you will see is that this macroscopic diffusion process is really an example of an ensemble of atoms that are jumping their way through the material at that atomic level. So the outline for today is that we're going to cover thermally activated atomic jumping. We're going to consider a couple of specific cases of particle jumping from a square well potential, particle jumping from a parabolic well potential, and then we will generalize the result from there. And this first part is just considering a single atom jumping. And then in the second half of the lecture, we will deal with diffusion as a series of discrete jumps. So instead of looking at a single atom jumping, we'll look at a whole collection, an ensemble of atoms jumping, and see how we can connect this atomic picture of diffusivity to our continuous picture that we dealt with in the earlier chapters of the book. So the atomic basis for diffusion can trace its origin back to Robert Brown's work back in 1827. He was a botanist who discovered that when he was looking at individual grains of pollen floating on the surface of water, that they seemed to undergo this type of random motion, such as shown in the path here. And this seemed to be unrelated to any type of convection of the water itself. And it took a long time for scientists to understand the reason for what we now know today as Brownian motion. The first person to develop the explanation was actually Albert Einstein, who understood that that this water that the pollen was floating on was actually made up of water molecules, and those individual water molecules were randomly bumping into the grains of pollen and causing this type of Brownian motion. So, ooh, bless you, Robert. Anyway, Brownian motion is a random movement of particles where the particles do not have a specific direction to travel. Instead, they move in all directions, and those are not governed by thermodynamic affinities such as chemical potential gradients. This is in contrast to diffusion. With diffusion, we still have particles that are jumping around, but there is a net direction which is dictated by their governing affinities, for example, their chemical potential gradients. The commonality between Brownian motion and diffusion is that in both scenarios, the individual particle movements are random. So the difference is that in diffusion, there is a governing thermodynamic affinity, and in Brownian motion, there is not. So what we've done up to this point has been considering a macroscopic description of diffusion. This is based on continuum equations for the fluxes of particles and the evolution of their concentrations. Of course, those are Fick's first and second laws. And the macroscopic description of diffusion involves defining a diffusion coefficient, d, also known as the diffusivity, which is the kinetic factor related to this diffusive motion. On the other hand, with a microscopic description of diffusion, here we're considering individual particle displacements. We're considering how each atom is jumping within the material. So this can be modeled as a series of thermally activated discrete movements, which are known as jumps. And the rate of these jumps depends on the vibrational frequency of the particles, the excitation energy that's required to make a jump, and temperature, or in other words, the amount of thermal energy that is available to those atoms. So thermally activated atomic jumping is the fundamental process in atomistic diffusion. And this is what governs the movement of atoms between neighboring sites of local minima. One of the common themes of jumping is that the duration of the jump itself is typically very short. because the transition state when making this jump is highly unfavorable. So the particle goes through that transition very quickly, but it spends most of its time in the local minimum sites at either side of the jump. The residence time depends on the probability that the particle will undergo a fluctuation large enough to surmount the activation barrier. Here's an example. This shows interstitial diffusion, where if we've got a crystalline lattice here of blue atoms, and let's suppose that we want to consider the diffusion of this smaller red atom that is occupying an interstitial site here between the normal sites of the lattice. In order for this interstitial atom to move, it needs to move between these neighboring interstitial sites. And that involves spending most of its time at an interstitial site. Each time it vibrates, it's bumping up against the atoms of the lattice. But if it has enough energy every once in a while to actually push apart these two atoms on either side, it may be able to squeeze itself between those atoms and fall into the neighboring interstitial site, where it then vibrates again until it has enough energy to push aside the two lattice atoms again and move to the neighboring site. And this process continues from site to site, not just with one atom, but with any number of interstitial atoms. And then if we looked at the collective behavior of the jumping of all these interstitial atoms, that is what gives the overall diffusion process according to this interstitial mechanism. This shows an example trajectory of a diffusion atom from a molecular dynamics simulation that was conducted by two of my students, Rebecca Welch and Colin Wilkinson. Here they're showing the trajectory of a diffusing atom where this initial part is vibrations in a local energy minimum, also known as a well state. So this is a low energy location for the atom. This is where one of the positions where it wants to be. So it spends a lot of time vibrating back and forth. And then after a while, it is able to go through this activated state shown here. It passes very quickly through this activated state since that is energetically unfavorable, and then falls into a neighboring well state where it undergoes another sequence of vibrations, then goes through this more tortuous activated state and falls into another neighboring well state. So the lesson is that most of the time the atoms spend in the lower energy states, these well states. But every once in a while, they're able to escape from those well states, become activated, and then travel to a nearby well state. So let's consider a simple model here for particle jumping in a square well potential. This will be considered as a classical potential, so not a quantum potential. So there's no quantum tunneling here, and we don't have a discrete number of possible states. But let's consider here the square well potential in a classical sense, where there are two energy levels. E well is the lower energy, which corresponds to the energy of the well state. This is where the particles are more energetically favored to exist. And then EA is the energy of the activated state. Now, the rate at which the particle traverses this activation barrier is going to be calculated first as a one particle event in one dimension. So in other words, how long does it take for a single particle to become activated, to come up to this activated state, and then to cross the activated state? So to label these different regions on the energy diagram, we have a well state here on the left, corresponding to this lower energy, and another well state on the right. And those two well states are separated by this activated state in between, which has a higher energy. We also have two relevant length dimensions. LA is the length of the activated state. So that's the distance that the atom would need to travel to get over the activated state. And then L well is the width of the well state itself. So the well states have low energy and therefore a higher probability of having the particles. The activated states have a high energy and therefore a low probability. Now, the jump rate is the inverse of the average migration time. So if we calculate the average migration time of a particle being activated and going across the activation state. The inverse of that would be the jump rate. And this average migration time depends on two things. First, the time that an atom waits to reach an activated state. And secondly, the migration time in the activated state. So we're going to consider both of these two individually and then combine them together. So first, let's consider how much time does it take for an atom that's already activated to cross over this activation barrier that has a width of LA. The average crossing time is denoted here as tau cross, and this can be written as just the distance that the atom needs to travel, LA, divided by the average velocity of that atom. So simply the time is equal to the distance that needs to be traveled divided by the average velocity. Now we can rewrite the velocity in terms of momentum, and then the average crossing time becomes the distance that needs to be traveled times the mass of the particle divided by the average momentum. Now, the next thing we need to do is to calculate this average momentum. And we can do that using the underlying statistical mechanics, where the average momentum specifically in the positive direction, because if the atom becomes activated from, say, the left-hand well state, it needs to travel in one specific direction to reach a neighboring state rather than falling back in the previous state that it occupied. So if we consider that it needs to travel in the positive direction, then the numerator here would be the integral from 0 to infinity to give us the average momentum in the positive direction. So it's the integral from 0 to infinity of the momentum, then times our Boltzmann probability factor, and then integrated over the momentum. The Boltzmann probability factor is e to the minus, in this case, it's the kinetic energy, over kT. So it's e to the minus momentum squared over 2m, and that is divided by kT. And if we then normalize this to the integral over all momentum space, so this integral from minus infinity to infinity, this is like the partition function here. This then gives us, solving these Gaussian integrals, gives us the average momentum in the positive direction, which turns out to be the square root of mkt over 2 pi. So this is the square root of the mass of the particle times Boltzmann's constant times the absolute temperature divided by 2 pi. So now taking this quantity for the average momentum, we can stick it into this equation for the average crossing time. And then the average crossing time is therefore this distance that needs to be traveled times mass divided by the average momentum. And that is equal to LA, the width of our activated region, times the square root of 2 pi m over kT. Now, if we have a system of n particles, the total rate at which the particles cross the barrier is this n cross dot. The dot here indicates a time derivative. This would be the number of particles in the activated state divided by the amount of time that it takes for them to cross the activation barrier. Assuming that each of these particles are acting separately, so independently of each other, this would just be the number of particles times the jump rate for a single particle, this gamma shown here. Or in other words, the number of particles times the fraction of time spent by a particle in the activated state. So this would be the amount of time in the activated state relative to that in the well state, divided by the amount of time that it takes to actually cross the activated state. So for a single particle, the jump frequency has two parts to it. It has this ratio of time spent in the activated state, and for each particle that's in the activated state, how much time does it take to cross? So we just calculated this tau cross. The next thing that we need to calculate is this tau A over tau well. And this likewise can be calculated from the underlying statistical mechanics, where the ratio of time spent in the activated state versus the well states is just adding up all the probabilities of being in the activated state. So this is a summation over all the activated states with our Boltzmann probability factors here, e to the minus EA over KT, and then divided over the same thing in the well states. Since we were dealing with a continuum, we can rewrite these summations as integrals, where the upper integral is over all the activated state, and the lower integral is over all of the well states. And this, then, when you put in the activated energy in the numerator and the well energy in the denominator, this is just the ratio of the width of the activated state over the width of the well state times e to the minus then the energy difference between the two states, the delta E, E activated minus E well divided by KT. So this factor here has two parts to it. It has the energetic piece that follows this Boltzmann probability factor, e to the minus energy difference over KT. And then it has the entropic piece out in front. So that is the prefactor that tells you basically how much space does a particle have to occupy the activated region versus the well region. So if we put all of this together, the single particle jump rate is therefore this gamma equals tau A over tau well. That is what we just calculated here, times 1 over tau cross. This is what we calculated previously. So plugging this all together, what we have is that the single particle jump rate, gamma, is 1 over L well times the square root of KT over 2 pi m times e to the minus energy difference over KT. There are two parts to this equation. The prefactor in front of the exponential is an effective average attempt frequency. This tells you like how many times the particle attempts to overcome the barrier. And the probability of success at each of those attempts is given by this Boltzmann probability factor. So the vibrations out in front are governed by the geometry of the energy well, the L well. It's governed by the temperature of the system and by the mass of the particle. Higher temperature would indicate a higher rate of vibrations for the square well potential. A larger mass would be a lower rate of vibrations. So this prefactor determines that vibrational rate, and then the probability of success for each vibration and actually becoming activated is given by this Boltzmann probability factor. A higher temperature would be a higher probability of success, or a lower energy barrier would also indicate a higher probability of success. So that is just one simple example with a square well potential. What if we make this slightly more complicated and consider a parabolic well potential? In this case, we're considering the activated state to be the same as before, where it has an energy of the activated state equal to EA and a width of the activated state equal to LA. But then instead of having a square well potential, we're going to assume that the well state energy is being described by a parabola, where it's E min, so the minimum energy of the well, plus then our curvature here, beta over 2, times x minus x min squared. So this is the parabolic part. And this parabola continues until the energy reaches the activated state, at which point it is assumed to be flat. Now, the time that it takes an activated particle to cross the activated state is exactly the same as before, since the activated state in this case is the same as what we assumed with the square well potential. What's different is the tau A over tau well factor. And now we just need to update our integrals here. The numerator is the same as before, since the energy in the activated state is a constant as before. But in the denominator, we need to update the energy to account for this parabolic form. And so once we update this integral and solve for this is another type of Gaussian integral. What we have is that the ratio of the tau A to tau well is equal to LA, the width of the activated region, times e to the minus energy difference over KT, times now the square root of beta over 2 pi KT. So now notice that the beta here is the shape factor. That is, how large of a curvature do you have? Now, if we combine all of this together to get the overall jump frequency gamma, this is tau A over tau well times 1 over tau cross. Tau cross is exactly the same as before. So taking this term up here, and then dividing by the tau cross, this gives us the overall jumping rate for the particles in the parabolic well potential, and that is 1/2 pi times the square root of beta over m times e to the minus energy difference over kT. In comparing this to the square well potential, you'll note that the geometry factor is now related to the curvature, where this attempt frequency out in front no longer depends on temperature with the parabolic well potential because of the harmonic shape, but instead depends on the curvature of the well, where a larger curvature means a higher frequency. The dependence of the vibrational frequency on mass is the same as before. The vibrational frequency will decrease as the square root of the mass increases. And then our success rate is the same as before, where it's e to the minus energy difference here between the activated and minimum energy states divided by kT. So if we compare these two, the upper equation here shows our jump frequency for the square well potential. And the second equation is the parabolic well potential. The Boltzmann factors have the same form. And then the prefactors that give the vibrations have some slight variations where the square well potential depends on the temperature of the system. And with the parabolic well potential, it doesn't. It only depends on the curvature and the mass of the particle. Now, these top two equations involve some specific geometries of the wells. We can generalize from this, and so the way that you will most commonly see the particle jump frequency expressed is according to the bottom equation, where the jump frequency gamma is equal to some attempt frequency, which is usually just labeled as nu. This would be your attempt frequency. Whatever it is, whether it depends on temperature or not, depends on mass, depends on whatever geometry factors, all of that gets incorporated into this attempt frequency nu. Each one of these attempts, each one of these vibrations is like an attempt to overcome the barrier. The probability of successfully overcoming that barrier is this Boltzmann term, which is e to the minus barrier that needs to be overcome. So that's e to the minus activation barrier divided by kT. In other words, how much energy is required compared to the amount of thermal energy that is available in the system. A higher temperature would be a greater probability of success, and a lower activation barrier likewise would be a greater probability of success. So that is for a single particle. In order to get the overall diffusion behavior, we have to consider the collective behavior of a large ensemble of particles, or alternatively, take a single particle and run it through many different realizations to see all the different paths that it can take. The normal approach is to consider a large ensemble of particles and see, in a statistical sense, how are they evolving over time. And if you can track say the displacement of these particles over time, that can be related to the overall macroscopic diffusivity. So let's consider if a particle jumps with an average frequency of gamma, and let's suppose that we watch it jump over a time tau. On average, how many jumps will it actually execute? It's simply the product of those two quantities. So the number of jumps that it is expected to take, n sub tau, is equal to the frequency, the jump frequency, times the amount of time that we have. So it's gamma times tau. Now, the total displacement of the particle is going to be the sum of the individual displacements. So if every jump has an individual displacement of this little r sub I, and now if we sum up all of these individual displacements over all n tau of our jumps, what we get would be the total displacement vector after n tau of those jumps occur. Now, the random walk process can then be described by the distribution of total displacements for either a very large set of these non-interacting walkers, or a very large set of particles, or repeated trials of an isolated walker. So here are some useful quantities to keep in mind. First is the total displacement of the particle. The total displacement of the particle is simply the summation of all the displacements of each one of the individual jumps. If we take the average of that, we can get the average displacement vector. But the more useful quantity is what's called the mean squared displacement. The mean squared displacement is a scalar quantity that characterizes the diffuseness of the distribution of how the particle is spreading out from its initial position. The mean squared displacement is usually represented as shown here, where it is an average here. So these angle brackets indicate an ensemble average. This is an average of the squared displacement, or in other words, an average of the displacement vector dotted with itself. So if we take this displacement vector dotted with itself, then the squared displacement can be rewritten as the dot product of every individual jump displacement with each other, and summing up all of those. So each one of these total displacements is the summation of individual jump displacements. So dotting this quantity with itself involves adding up. See, there's a diagonal term here, which is each individual jump displacement dotted with itself. Those are always in the same direction because they're the same vector. But then the off-diagonal terms are the individual jump displacements dotted with each of the other individual jump displacements. So sometimes these jumps are acting in the same direction. If they're acting in the same direction, then the particle is able to travel a greater net displacement. However, sometimes the particle might just be jumping back and forth between one site and another site, such that the net displacement is very small or even zero. So what we can do is actually combine all of the diagonal terms together, and we get this first summation here, which would be all of the terms along the diagonal. And then the second summation is all of the terms along the off-diagonal. And another way to rewrite these off-diagonal terms is in terms of the cosine of the angle in between those individual jump vectors. And this cosine accounts for whether these jumps are in the same direction, in opposite directions, or whatever angle they happen to be with respect to each other. So if we have then the squared displacement for one particle that has these two terms, which is the diagonal term and the off-diagonal term. We can also define this mean squared jump distance, which is just in terms of the diagonal term as shown here. But if we average over a large number of particles, the quantity that we're really after is the mean squared displacement. The mean squared displacement after n tau of these jumps has the diagonal contribution shown here, as well as the off-diagonal contribution. Now, why do we have this quantity? Einstein was the first scientist to connect the atomic scale physics of particles jumping with the macroscopic physics of diffusion. And the way he did that was via the mean squared displacement. So on the left here, this is the mean squared displacement of the particles. And he connected that to the macroscopic diffusion equation by having the solution of Fick's second law, so the solution of the diffusion equation in a macroscopic sense, for a system where all the concentration starts at an individual point, and then the concentration spreads out radially from that point. And this is the solution that we already had from chapter 4 for either a point source or a plane source. It is just this Gaussian description shown here, that the concentration that is initially concentrated at a single point is going to spread out following this Gaussian function over time. And this can be solved in 3 dimensions, which would mean spreading out as a sphere in 3 dimensions, in 2 dimensions, which is spreading out as a circle, or in 1 dimension, which was the original problem that we solved at the very beginning of chapter 4. And if you solve these in any of those 3 types of dimensionalities, what you would see, what Einstein found, is that the mean squared displacement is equal to, by comparing these solutions, either 6 dt for the 3-dimensional case, 4 dt for the 2-dimensional case, or 2 dt for the 1-dimensional case. In other words, it's 2 times the dimensionality of the space times the diffusion coefficient times time. And the mathematical trick that enabled him to do this is what's called calculating the second moment of this concentration function. So taking the solution here, the mean square displacement of the particles is equal to the second moment of this concentration function, which is defined here. So it's integrating over r squared times the original function. And in spherical coordinates, this 4 pi r squared gets included as the surface area of the sphere. But what is this moment of a function that Einstein used? I want to take a few moments here to give you a math moment on moments of a function. And this is a very general mathematical concept where if you have any properly normalized function f of x. By properly normalized, I mean if you integrate it over all space, that integral equals 1. In other words, this f of x is a probability density function. No matter what this probability density function f is, the moments of that function give us the properties about how that function is distributed across space. Now, we can generally define the nth order raw moment of a function as shown here, where the nth order raw moment is this mu prime sub n, where n is the order, and this is equal to the integral of x to the n power. So this is our variable here, x raised to the power of the order of the moment times our function, f of x, integrated over x space. For example, if we have the first moment, the first order raw moment of the function, this is equal to mu1 prime, and this is equal to the integral of x to the 1 power, so just x, times f of x times dx. And this integral, of course, is just the mean of the function f of x. This mean of the function is more commonly represented by these angle brackets shown here. So this first order moment is telling us something important about the function, which is its mean value, mu1 prime. Now the higher order moments, the second order moment and so on, are normally calculated as central moments rather than raw moments, where a central moment involves x minus the mean. So it's always the x value relative to the mean in this case, where the central moment, the nth order central moment, is mu sub n without the prime, just mu sub n equals integrating over all space x minus the mean raised to the nth power times the function f of x. For example, the second order central moment is shown here. The second order central moment is mu sub 2. This is the integral of x minus the mean squared times the original function integrated over x. This can also be rewritten as the function minus the average of the function squared, and then average over that quantity. And this is more commonly denoted as sigma squared, which we all know as the variance of the function. So the variance of any function is just the second order central moment of that function. And if you take the square root of the variance, what you get is the standard deviation of that function. The standard deviation is just the square root of the second central moment of the function. So sigma is equal to the square root of mu2. That's equal to the square root of this function minus the average of the function squared, average of that. Or in other words, it is the square root of the integral of x minus the mean squared times the function times dx. So the first order raw moment gives us the mean. The second order central moment gives us the variance. If you were to take the first order central moment, that's just the mean minus the mean, so that is 0. But if you go to these higher order central moments, this gives us more information about the function. The third order central moment is the skewness of the function. This tells you how asymmetric the function is. The fourth order central moment gives you the kurtosis. That is how much of the distribution is in the tails of the distribution. You can keep going more. The fifth order moment is the hyperskewness. That's more information about the asymmetry. The sixth order central moment is the hypertailedness, which has more information about the shape of the tails of the distribution. And you can keep on going and calculate as many of these moments of the function as you would like. Every time you calculate these, you're learning some more information about the shape of the function. Now, normally, as scientists and engineers, we stop after the mean and the variance, sometimes even after just the mean. The mean and variance are the two most useful quantities. Skewness is also very useful because it tells you asymmetry. Tailedness or kurtosis is also very useful. But if you keep calculating these moments, you can have a complete description of the shape of that function. And so what Einstein did was to use the second order central moment, so the variance, to calculate how much of a spread that we have of this concentration function as we are solving this equation, and then relate that back to the mean squared displacement. And in case you're wondering about the meaning of the cover art here, the cover art of the book, this beautiful cover art, it's not only a beautiful work of art, it also has great mathematical meaning. And this was designed by my good friend here, Dr. Jane Cook. This is some artwork that she made back in 2018, and it's called Moments in Love, Mean Variance Skew Kurtosis. It's originally acrylic and tissue paper on canvas. You can see the original artwork here hanging up on the wall. And she developed this as a word, so it's a painted collage. It's a wordplay on the title of the song called Moments in Love, which is by the 1980s new wave band Art of Noise. The canvas is painted red and overlaid with crinkled red tissue, over which four roughly rectangular forms are positioned, essentially squared with each other in the canvas. This is her description here, that the piece is the artist's nerdy commentary on the utility and futility of analysis in matters of the heart. One might find joy amongst the scattered undulating hills and valleys of the underlying function of love without knowing more details of that function, or one can deploy a knowledge of statistics to extract the moments of the distribution of highs and lows. Neither method of experience is superior. They each provide unique insights. And here is the artwork without any of the text on the front. You can see her signature here. And these kind of rectangular patterns are meant to represent the different moments of the function. So the mean, the variance, the skewness, the kurtosis, and so on. And so that's why this is used as the beautiful cover art for the book. Now, Einstein's diffusion equation is just one way of connecting the microscopic and macroscopic physics of diffusion. Another way is to consider the statistics of a random walk on a type of landscape. A random walk is when a particle moves by a series of displacements, each of which is independent of the one preceding it. So for example, if we are here on this one-dimensional landscape, where we're starting at this middle position here, 0, and let's suppose there's some probability of jumping to the right, which is PR. There's a probability of jumping to the left, which is PL. NR is the number of positive displacements, and L is the number of negative displacements. Given this information, the question is, what is the probability of occupying this site little n after a total of n tau number of jumps? In other words, if the particles undergo NL number of negative displacements and R number of positive displacements, according to these probabilities, what's the probability of ending up in some particular site here, little n, after a certain number of jumps? So these must satisfy the following conditions. NR minus NL equals little n, because if we want to end up at this little n site, the number of displacements to the right minus the number of displacements to the left must equal this little n. So we're jumping to the right so many times, then we're jumping back to the left, and the difference between the two has to let us finish in this site little n. Likewise, the total number of jumps to the right and the left has to equal the total number of jumps, so NR plus NL equals N tau. And the statistics that governs this is just binomial statistics. This is exactly the same as if you're to do a coin flip, where let's say getting a heads is equal to making a displacement to the right, getting a tails is equal to making a displacement to the left. This is just binomial statistics, so the number of ways is governed by this formula here. And if we use this combination of NR and NL, substitute that in for NR and NL here, then we have this distribution here in terms of n tau, the total number of jumps, and this little n. So it's n tau factorial over n tau plus little n divided by 2 factorial, and then n tau minus n over 2 factorial. And therefore, the probability of occupying the site little m after n tau number of jumps is just equal to that factor times then our probability factors of actually moving to the right that number of times and moving to the left that specific number of times. If it's a fair coin, or in other words, if the probability of making a right jump is the same as making a probability of a left jump, then they're both equal to 1/2, and then this is just 1/2 to the n tau power. Now, how do we connect this then to macroscopic diffusion? If you consider the coin flip problem, the binomial distribution and the limit of a very large number of coin flips becomes the Gaussian distribution. So that the binomial distribution is a discrete version of the distribution that in the limit of an infinite number of events converges to the Gaussian solution. So if we consider this very large number of jumps here, n tau, this binomial distribution becomes a Gaussian distribution, which is the same as the solution of our continuous diffusion equation from Fick's second law. And therefore, this equivalence of the Gaussian distributions in both descriptions is another way to connect the microscopic and the macroscopic physics of diffusion. So to summarize, macroscopic diffusion is the result of microscopic jumping of particles. The rate of jumping depends on 2 factors, the vibrational frequency and the activation energy. The shape of the potential energy well can affect the kinetics of the diffusion. And diffusivity can be described in terms of the mean squared displacement of particles following a sequence of jumps. Next time, we're going to take what we've learned here and apply this to a real crystal. So that will be coming up next time. So till then, I will see you later. Thank you very much for listening.